Okay, so now that we have our formulas for our approximations for the first and second derivatives, we need to set up grids for the heat and wave equations, and then also for Laplace's equation. So for the heat and wave equation, these are time dependent. They have a t term. And so generally we'll look at the first order, we'll look at one variable versions of this. You can do multiple variables, but we'll just look at one variable. So for both the heat and the wave equations, the idea is that you have, this is your domain for your u of xt, right? Time goes up and x runs from 0 to L. So in the heat equation, we imagine we have a bar of length L, and we want to know what's the heat inside of it. In the wave equation, we think we have a string of length L tied down at 0 and L, and we want to know if we start it in motion, what happens to it. So what we're going to do is break up the x distance from 0 to L into a bunch of little segments of width delta x, right? So this point is delta, this is 0, this is 1 times delta x, this is 2 times delta x, 3 times delta x, dot, dot, dot. And then this becomes, this point here is I times delta x, dot, 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 and we get to the end. For t, similar thing, we will dot, 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 break up the time axis, dot, dot, dot. It just goes up to the future, into bits of width delta t. So this is 1 delta t, 2 delta t, 3 delta t, dot, 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 4 delta t. Well, no, we don't know what that is because we did dot, 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 but this we'll call j delta t. And so that puts a grid on our domain, right? And in the middle, we have this point, and this point is I delta x. So whatever our number I is, that's how many delta x's you've gone to the right, and j delta t. So that's how far in the future you are. And we want to know what is u at that point, right? So what we're going to do in our approximations for the heat and wave equations is we're going to find a formula that says, if I know the values at an earlier time, right? If I know these values, I can figure out how they affect this point, the temperature or the motion at that point, in terms of these three, and those are determined by the 3 time elements before them, et cetera, et cetera, et cetera. And so everything comes down, can be traced down to this. What is your initial conditions here? What are your conditions on the side? So along the bottom, let me draw a slightly a similar picture down here. Say we think of just as the domain like this. This is 0, this is L, this is T going up, this is X. All along here, that's my initial condition. So I know the values of U along this particular line. All up and down here, these are the boundary conditions. So I know the value of U everywhere in here. And what that means is that if I discretize it, I can get the value of U for one time step, and then the value of U for another time step, and then the value of U for the next time step, and just work my way up in time. The notation we're going to use, though, is that rather than this, which is a little bit, rather than this thing, which is a little bit complicated, not complicated, it's just involved. We'll call it ui sub j. So the first component is the x component, the j refers to the time component. Okay, so graded notation for Laplace's equation is a little bit different because Laplace's equation doesn't have a time element. And so it's just really a box, really, that goes from 0 to A and from 0 to B. And then likewise, dot, dot, we can divide this up into a grid, dot, dot, dot. And this is I delta X. Each one of these is a width delta X. And then doot, 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 dot, 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 doot, 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 dot, 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 doot, doot, doot. And then they'll call this J delta T. Each one of these has a width delta T. So that breaks up my rectangle into a grid. And of course, we have the same point, I delta X, J delta Y. I'm sorry, that should be a Y. And we want to know what is U of I delta X, J delta Y, or again, we'll call that UIJ. I is the X coordinate, J is the Y coordinate. But for this point, we're going to have to use these 4 points, right, to determine what's going on there at that point. And then this one, well, say this one here, that'll be determined by these points. And you can see that that works its way out to the boundary. And remember, the Laplace's equation, which is thinking about heat in a steady state, all along the boundary, right, we know what the temperature is. And we want to know, can we figure out what the temperature is in internal is? And it's a little bit trickier than the than the wave and heat equations, because there's no time direction. And you have to figure out how the information from the boundary propagates inward. And that involves, on the one hand, you can solve it because it's just a bunch of linear equations, and you get a big matrix and you have to invert it, and that's not a big problem, unless you really want to have thousands and thousands of these things. Or you can do what's called an iterative method, and we'll take a look at both of those when we do Laplace's equation.